When you flip a fair coin 10 times, what's the most likely number of heads? Well, since heads and tails are equally likely, you can probably figure out that the most likely outcome is that 5 come up heads, 5 tails. Say I offer you a bet. If it is exactly that result, I'll pay you $1. Otherwise, you'll pay me $1. Should you take the bet? To answer this, we'll have to find the probability a binomial random variable x with those parameters, 10 flips, each with a 50% probability, results in an outcome of 5. We would express this as PRx equals 5. One way to find out is to simulate many draws from x, say 100,000, and then see how common each outcome is. As you saw in the last exercises, you can choose the number of draws to perform by setting the first argument of rbinom. This resulting variable flips then contains the result of these 100,000 draws. We can't print out all these results, at least not in a way we'll understand them. Instead, we can visualize them in a graph. This plot is called a histogram. Each bar shows the relative frequency of one outcome, from 0, 1, 2, all the way through 10. Histograms are a common way to examine a probability distribution, and we'll be using them frequently throughout the course. Notice that out of these 100,000 draws, about 25,000 are equal to 5. There's a useful trick in R for calculating the fraction equal to 5 directly. The expression flips equals 5 compares each item in the vector to 5. We can then use the mean function to find the fraction of comparisons that are true. This works because the mean function treats true as 1 and false as 0. Thus, mean flips equals 5 gives the fraction of values equal to 5. You're going to be using this trick with mean a lot in these exercises whenever you estimate values through simulation. In this case, we found that the fraction of outcomes equal to 5 was 0.2463. That is, there's a 24.6% chance. This is called the density of the binomial at that point. Simulation is a very useful way to understand a distribution and to answer questions about its behavior. But in the case of the binomial distribution, R also provides a way to calculate the exact probability density using the dbinom function. Dbinom takes 3 arguments: the outcome we're estimating the density at, 5, the number of coins, 10, and the probability of each being heads, 0.5. Notice that this gives a result of 0.246. This confirms the result from our simulation of the probability. Similarly, we could calculate the probability density of getting exactly 6 heads, or all 10 being heads, by changing the first argument. Finding a probability through both simulation and exact calculation will be a common task in this course. So now you know not to take my bet. More likely than not, we won't get exactly 5 heads out of 10. What if I offer a new bet? I'll pay you $1 if 4 or fewer come up heads, otherwise you have to pay me. This describes the cumulative density of the binomial. The probability x is less than or equal to 4, and the process for calculating it is similar to calculating the density. You can estimate it using simulation. We generate 100,000 draws from the binomial distribution, then instead of using equals, we do mean flips less than equal to 4. You can see that this was true of about 37.7% of the simulations. Much like the density, R provides a function to get the exact cumulative density of the binomial. Rather than dbinom, use pbinom. This result confirms that the probability is about 37.7% that a binomial with 10 flips gets 4 or fewer heads. In other words, you still shouldn't take my bet. In your exercises, you'll find the density and the cumulative density of several other binomial distributions using both the simulation approach and the dbinom and pbinom functions.